Hems, they are everywhere on garments and are a key detail for realistic cloth. But between seam-constrained, self-collision and folded fabric, they are really a pain to simulate and animate properly. So could we find a way to create them entirely procedurally after simulation and animation? The answer is yes, and it works surprisingly well with any kind of animation as long as you have a properly UV unwrapped model. Working in UV space, which is always stable, we can create geometry on top of the usual modifier stack, and we can dial every aspect of it, as well as create custom UV space for seam puckering shading and precise effect near the seams. Combined with edge top stitches from the previous tutorial, which will be part of the same asset pack, we can work towards a fully procedural and animation stable cloth making toolbox. So let's get to it. For this tutorial, I am going to use this shirt 3D model, which was kindly shared by my friend Virgil Bioza, who is also advising me on the development of this asset pack. Because it was made using Cloth 3D, each mesh island corresponds to one UV island. But if it isn't the case on your model, you can simply add the geometry node setup from the previous tutorial to procedurally split all the UV island into different mesh islands. Now let's go to the geometry node tab and create a new GeoNode setups. I'm going to call it Group to Hem. Now I am first going to select a few edge groups to create my hems. So I create a new vertex group. In edit mode with Alt-Shift-Select, I am selecting a few edge groups on which I create my hems, and I assign them to my vertex group with a value of 1. Now that we know where we want to put our hems, let's begin the setup of everything. We are going to use a bunch of repeat zones to first iterate over all the different mesh islands, and then to do the different steps to extrude our hems. This whole setup might get quite expensive to compute, so we are going to do a bunch of optimization to everything. First, I will only select the mesh island on which I have some hems, on which I selected my hems, so we do not iterate over all the other mesh islands. To do that, we can use a separate geometry node, set to points, and to differentiate the mesh island on which we created our vertex group, we can use an accumulate field node, set to float endpoint, and put the total value into the selection input of our separate geometry node. For the group ID, we want the island index of the mesh island node, and for the value, we can create a new input, which is going to be our selection. Here we can switch to attribute and select our hems. Now if we take a look at this value, we will only have a white value where we have our hems, because this will accumulate the value of our selection over all the mesh island, because we are separating the group ID by the island index, and if the value is greater than 0, it means that somewhere we selected our vertex group, and this allows us to separate our geometry, just like this. So we'll only do our processing on this selection, but right away we can add a join geometry node in the end to add back our inverted selection. Now to iterate over all our mesh islands, we first need to capture the island index for each part, so we can add a capture attribute node set to integer and duplicate the mesh island node, so we can plug the island index right here, and the island count will be the number of iteration of our repeat node. Right away it won't work, because this is a field and we only need one value. To do that very easily, we can add a sample index node, set to integer endpoint with our selected geometry, and here if we plug our island count into the value and the output as the iteration count, it should work. Let's plug our geometry into the repeat zone and replace the result of this in our join geometry. As the final step for this base setup, I'll just store a named attribute for our processed geometry, which will just be a boolean value called processed, which I will set to true on the branch that we will process. Ctrl J, frame everything, and this is the base setup. Now let's tackle the repeat zone. At each iteration of the repeat zone, we only want to process one mesh island. To do that, we need to compute the current iteration of the repeat zone. So if I select the input, I can add a new input, which is going to be an integer, and I am calling it iteration. It can start at 0, but then each time we'll add a value of 1 with a math node like this. And now that we know the iteration, we can compare this to the island index and separate the geometry. So let's add a separate geometry node, and for the selection we can check if this is equal to the captured island index from before. So right now we just lost the output, and this is because we are piping the selection into the input of the repeat zone, and once we selected a mesh island for one iteration, it won't be able to be computed into the next one. So here we don't get any value. To fix that, we could add a join geometry node like this. So now if we inspect this and change the inspect index, we can check that we get each of our 3 mesh islands in this case. But this is not really efficient, because at each iteration we'll check the mesh island index for the whole mesh, even for the parts that we already processed. So a more efficient way to do this would be to only pipe the inverted selection into the input, so that on the next iteration we'll only check the mesh that wasn't processed yet. And now we can add another input like this, which will hold all the processed geometry. And if I put this new output in the join geometry in the output, we get the same result as before visually, but you can trust me, it will be much more efficient. Now we can rename this processed, and here we will do all our computing at this point of the data flow. Let's clean this up a bit and make some room for what we will add next. Now let's separate the edge loops where we want our hems. Let's bring our group input, and in our repeat zone, right after the separate geometry node, we can add another one, and we are just going to plug in our selection in the selection input. So now at each iteration, we get our selected hem edge loops. To work with it better, we need a few attributes. So add a capture attribute node, set to vector, and here we want the position. Now we are going to move to the UV space, so we can work with our hems better, and independently of any animation. So because the UV coordinates are stored in the face corner, we can't do it after the separate geometry node, because right here we only have points and edges. So right before that node, we can add a set position node, and we can plug the position as a new group input, which we are going to name UV map, and with the default attribute of UV map. Now in the modifier stack, we can switch to attribute and select our mesh UV map. That way we moved our selection in the UV space. And then we can add a mesh to curve node. Now we can select all this and frame it with Ctrl J, just so everything stays together. Now the reason why we are working with curves in the UV space is so we can precisely compute the direction along which we are going to extrude our hems. And moving to a curve will allow us to get tangent direction of the curve, which with the cross product with the normal of our mesh will allow us to get a very consistent extrude direction for the hem, which is going outside of the edge of our mesh. But to do this precisely, we need to do one more step, which is to be sure of the direction of our curve, because the way Blender computes the mesh to curve node, we might get some curves in one direction and other in the other direction. So we need to do a switch, always get them in the same direction. We already did this precisely into the tutorial about the edge top stitch on leather, so you can go there for a precise explanation, but here I'm going to do it more quickly. So first we need a capture attribute node set to spline and integer, and here we just need the index, and then we are going to sample the middle point of our curves. So with a sample curve node, with the factor set to 0.5 and our captured attribute as the curve index, we are going to work with the position and tangent values. Let's keep in mind that we are working in the UV space, so everything is only on the X and Y plane. So here we can compute the cross product of the tangent with a vector with only one on the Z value, so that will get us a vector which is perpendicular to our spline direction, but only in the UV plane, and this we can add to the position at the middle of our curve. Here we can add a scale vector, so it will give us a threshold value that we can eventually adjust. And this I am going to add as a new group input, which will be the curve reverse threshold, and I'm going to put a really small value at the start, so for example 1 mm, and I'm putting this as a single value. Let's set it to the default value, and now this will basically move our curve in one direction, and here we are just going to check if this move point is still on the UV island or not, and if it is, we are going to switch the direction. So with this we can get our separated mesh from right here, before the group we did just before, and we are going to sample the UV surface. And here we are going to be interested into the isValid output. But first, let's set the attributes. The source UV map will be the UV map, and the value and sample UV are just going to be the output of our add node from before, like this. Now we are going to evaluate the isValid output over our whole spline domain with the evaluate on domain node set to boolean and spline. And after all this, we want to reverse our curve from here with this node, and at the selection we want the inverse of this isValid node. So we are just going to go through a boolean math not operation just like this. And this setup will ensure that we always get our curve direction consistently over all our mesh islands. Now we can also frame this, because this is another processing step, which we can label fix curve direction. And the block from before was just select curves. Now on this curve we need to do a third step of processing, which is to compute a bunch of attributes. So first we need to separate two cases. In the first one, our mesh will still be in the UV space, and on the second one we want to move it back to its original space. So for that we can add a set position node, and for the position we can plug in our capture attribute from the start of this step, right here in our select curve group. So right here our curve is back in its original space. Now here all the attributes will be computed from the point of view of our mesh island, which is this mesh right here. And to compute the values over the whole mesh, we are going to use sample nearest nodes. And for this we need two nodes. On one side the sample nearest node, and this always works in tandem with the sample index node, which you can put right here. If we check this, we'll see that we have an issue, which is that for some reason the sample nearest node doesn't work on curve. So just on this branch right before this node, we also need a curve to mesh node, and this will get rid of this warning. Now this node we can set to vector, and right here we can sample the curve tangent. So that's the first attribute, and then on the branch where we still are in the UV space, we are going to do a bunch more processing. First, let's also put a curve to mesh node and sample nearest node. And here we are going to sample three different values. So we can add some sample index nodes, and we are going to get our geometry right before the curve to mesh node. Now we can Ctrl-Shift-D duplicate this 2 times, so we have 3 nodes like this. The one on the top will let to float value, and the 2 other ones are going to be vectors. For the bottom one we are going to sample the curve tangent, just as before. Then we are going to need the position of the point, and then I want the length attribute of the spline parameter node right here. Now the 3 attributes which we need to keep in mind are still computed in the UV space of our mesh, will serve a very specific purpose, which is to create a custom UV space which will depend on the direction of the curve, and this will allow us to create really precise shading along our hems. And to do that we will need to compute a few values, so that for each point in the UV space we are going to get, for example, the distance attribute between the point of the mesh and the closest hem spline. We also need the distance of each point from the start of the spline, and we will basically project the position of each point of our mesh, which looks like this. And basically for each point of our mesh we are going to project its position along the normal and tangent of each point of the spline, so that the position of each point will be relative to its closest point, which will look a bit like this. And to do that, we need to do a bit of math with our attributes. So first, with the sampled position, we're going to get the difference of position between the point of our mesh and the sampled position. So this will give us, for example, this vector right here. And to get the projection, we need to apply a dot product between the vector we just computed and the curve tangent, and also between the position we just computed and the normal of our curve, which we are going to compute just like before, with the vector mass node set to cross product with a value of 1 on the z-axis. And now to create a custom UV map, we can add a combined XYZ node, and here we can plug our first value in the X input, the second one in the Z input, and the sampled length from before as the Z input. And this will be, if we add a reroute node with the label, this will be the UV of the hems. Now later we'll also need just the curve tangent right here, so we can also add a reroute node, which we are going to call hem tangent, and the third attribute, which we did not use yet, is this one, which will also be the hem tangent, but let's just rename the first one to UV space hem tangent, so we can differentiate those two. Now that we computed the three attributes, we can select all these groups, Ctrl J, join it, and this will just be curve-based attributes. Now at this point, we already did most of the processing. We almost only need to extrude our hems themselves. Here we want to have control over our hem length, thickness, and resolution in both directions, so let's add a few new parameters. On the input node, I will add two integers and two float values as distance, which I will all put as single values, and so everything is set up like this. Let's put some default values, so for example 1 cm for the hem length, 2 mm for the hem thickness, a length resolution of 3 and thickness resolution also of 3, and I will revert everything to their default value in the modifier stack by pressing backspace. Now with those new inputs, let's compute a few values, because if we have a cross section of our hem like this, here we have a turning point, which will be made of some segments that are straight like this, corresponding to the thickness resolution, and a few segments here for the straight part. So the only tricky part is for this curve section. We want to know the different angle values between two successive strokes, and the first one which is different, and also the length of each segment depending on the resolution and overall hem thickness. So let's get our group input and start by computing the length of each segment. So here the thickness resolution is 3, so that means that between our main fabric and the hem itself we have 3 segments like this, and we want to know this length. So for a regular polygon of radius r, the length of each side is 2 times the radius times the sine of pi divided by the number of sides, and in our case the number of sides is 2 times the resolution, and instead of 2 times the radius we'll have our hem thickness. So here we can compute the thickness resolution multiplied by 2, which will give us this. Then we can divide pi by this value, which we can then plug into a sine value, and finally multiply this by the hem thickness. And with a reroute node to make everything cleaner, we can rename this the hem segment length. Now for the angle, in a regular polygon which will look like this, the sum of all the angle inside is equal to n minus 2 multiplied by pi. So that means that if you want a single angle, we can divide everything by n, and in our case, just as before, we only have half of the regular polygon, so that means that our number of sides is in fact 2 times the hem resolution like this, which means that now we can simplify everything by 2, and we only have n minus 1 divided by n times pi for the angle between two successive segments. So you can subtract 1 to the thickness resolution, divide this by the thickness resolution itself, and multiply this by pi. And this is the hem segment angle. And finally, if you look closer here, the first angle is a bit different. And in fact, we need to add a small value to the angle we just computed to get this. And this angle is really easy to compute. If you take a look closer, this value is just pi minus the angle we just computed divided by 2. So the new value for the start will just be our angle plus pi minus our angle divided by 2, which is basically our angle plus pi divided by 2. So now we can take this value, add pi, and divide by 2. And this will be first segment angle. Now we can join everything with Ctrl J, and this is the hem thickness parameters. Now we can take this group, put it near the end, and make some room to extrude our hems themselves. To create the hem, we'll do this in two different steps. First, we'll do a series of extrusions for the thickness, and then another series of extrusion for the length of the hem. And we'll do this with two successive repeat zones in our first repeat zone. So let's add a repeat zone, which we are going to plug in between the selection of our separate geometry node from before and the join geometry node at the end. Let's put this near the end, and let's begin to set up this. With our group input, we can already put the thickness resolution as the number of iterations, and here we will also need to add a math node set to add a value of 1, and this will allow us, just like before, to track the current iteration count. So we can set it up like this, put it as an integer value, and rename it iteration. Now we can add an extrude mesh node and set it to edges. Let's also put the selection as an input of the repeat zone, and for this we'll just take our selection from the group input, check if it is greater than, let's say, a value of 0.5, and plug this as the selection. So now we should have a first step of extrusion. For the scale of the extrusion, we can right away plug our hem segment length, like this. We should already give a better result. And now let's set the offset direction. For this, before going in the repeat zone, we need to capture an attribute, which will be a vector, and this is a value we computed before, which is the hem tangent, right here. Now with this attribute, which is for now along the bottom of our mesh, we need to compute a vector which is in this direction, and tangent to the mesh itself. So for this, just as before, we are going to compute the cross product with the normal of our mesh. So we need our normal and cross product with the value we just captured. Now if we plug this into the offset vector, it will go straight down for now, but we need to rotate this value by the angle we computed before. So we can add a vector rotate node, set to axis angle. Here the axis will be the tangent value we captured before, so we can rotate this vector along this one, and for the angle we can take our two hem segment angle values, and here we just need to check if the iteration is equal to 0, so if we are in the first iteration, then we can go into a switch node set to float, so if we are in the first iteration we get the first segment angle, and otherwise we just get this hem segment angle, and you can plug this into the angle of this node like this. And finally, we want to take the top attribute of our extruded mesh and plug it into the selection output of our repeat zone, so that we can extrude our mesh back onto itself multiple times. And here I just need to flip the input of the cross product node, so we get everything into the right direction. And now if we take a look at our result, we should have the first step of our hem at the bottom. And as you can see, everything is working really well for the first step of extrusion of this mesh. Now we can frame all this as the hem thickness extrusion. Now we can repeat pretty much all this for the hem length extrusion. So let's just select everything, which we can duplicate. Here we won't need the capture attribute node because we'll pretty much take the same value as before. So we can plug this whole group right after everything we just did. So let's take the geometry output from before, plug it into the input, and the output can take its place into the final join geometry node. Now we can rename this the hem length extrusion, and we'll just need to change a few values. For the iteration count, we need to plug in the length resolution. The offset scale of the extrude mesh can just be the hem length divided by the length resolution, like this. And for the selection, we can take the selection output of everything we just computed. As the input of our cross product, we can take the same captured attribute as before. And now we just need to set the value of this switch node for the angles. So for the first iteration, we'll also need the first segment angle from before. And for the other one, we just need a value of pi, so we can extrude everything straight up. And this is pretty much it to extrude the hem itself. We just might want to add a correction step, because if we take a look at everything, even though it will always work for the hem thickness, here we are just extruding the length straight up, so we might get some big gaps between the base mesh and the hem. But you can correct this with a really small correction step by adding a set position node right after the extrusion. For the selection, we can take the top output of the extrude mesh, and now we'll just need to compute the position and offset to make sure that the hem will always be extruded at the same distance from our base mesh, whatever the angle will be. And to do this, the easiest way I found is to do a sample nearest surface from the mesh right before our capture attribute node from before. That way we can sample two vector values, which will be the closest position on our base mesh and the closest vector on our base mesh. Here we can right away set the sampled position as the position of our set position node. So this will always stick our extruded hem onto the base mesh, and now we need to offset it by the normal scaled by the hem thickness. So here we can scale by some value, and for the value we can just take our group input, and because the normal is facing outward, we need to take the hem thickness, multiply it by -1 and plug this right here, which we can now plug into the offset of our set position node. And this will ensure that the hem will always keep its thickness whatever the mesh deformation will be. So now we can also include this into our frame, so everything is a bit cleaner. And now we only have a few things left to do, which are to correct the UV of the base texture around this new extruded part, and to set up the final output attributes. Now let's tackle the UVs on the newly created geometry. So to see it better, I'm going to quickly set a simple shader. Here I'm going to take an attribute node, set to UV map, and I'm going to create a new image texture, set to color grid, and make sure to save it on the side. Now we can plug it like this and preview the grid. So now, if your model was set up correctly, you should be able to see the UV grid properly everywhere, except on the newly created hems, where it should be really stretched. And now, the trick to get it correctly on the hems is really simple. We are just going to do about the same extrusion step, but on a version of the mesh that was put in UV space. And then by sampling the index, we should be able to transfer the UV coordinates from the unwrapped mesh to our original mesh. So the first step is to make a branch in parallel of our two extrusion steps from before, so right before the capture attribute at the start. And here we are going to set the position, and you guessed it, we are going to set it to the UV map from the start. Then we can capture an attribute, which is a vector, and it will be the UV space hem tangent, which we calculated before. And now we already have everything we need to do the extrusion steps. So let's add a repeat zone again. And this time all the steps will be the same, so we don't need to add one to each iteration and check it. So we just need an extrude mesh node, set to edges and we can put the selection as a new input. Here we can once again take our selection, make sure it is greater than 0.5 and plug this into the selection. Let's also plug the geometry and the thickness resolution as the iteration count. For the offset, we can take the cross product of our capture attribute with a vector with only -1 on the z-axis because we are in UV space, and the offset scale will just be the hem thickness divided by the thickness resolution. And now we can also repeat this for the hem length with our selection like this. We can take the same offset direction and we can take hem length divided by length resolution for the offset scale. And now if we take a look at this, we should have our flat version of the mesh with the newly created geometry at the bottom right here. We can frame all that and rename it UV space extrusions. And here make sure to set the length resolution as the iteration count and properly output the top selection. Now to work with those, we need to transfer them from inside our main repeat zone to outside, and here the easiest way is to add a new item to the repeat zone just as the process geometry, but this will be for the flat geometry. And then we'll also need an attribute which will be a vector, and this will be for the UV map. Now for the flat geometry, we can add a join geometry node with the output set like this, and we will be able to join the flat geometry we just extruded with the flat geometry from the repeat input. And to output our UV map, we can add a capture attribute on the newly created geometry set to vector, and this will be to transfer the data of the proximity UV map we computed at the beginning. So we can take our UV hem, put it in the capture attribute, and then we'll be able to add this to the UV map from the previous iteration, which we can get at the start of the repeat input. That way we will be able to output this UV map from all the iterations. And let's just rename it to UV Hems for clarity. Now we have everything we need to compute the final attributes, which will be to basically just transfer this new data to our base mesh from the processed data line. Let's add a capture attribute node set to vector, and here we are going to fix the main UV map for which we just created a texture to visualize. So right here we want to sample by index the flat version of the processed geometry set to vector and face corner. You can also put face corner on the capture attribute node, and here we are just going to capture position with the index being the output of the index node. And to output this, we need to combine this new geometry with the data of the unprocessed geometry. So we can also add the capture attribute on the second branch, and here we can capture the data from the group input UV map, and now we can add those two together to combine them, which will be able to export like this. On the group output, make sure this is a vector set to face corner. We can rename it UV map and with the default attribute of UV map. And now the UV map is properly set up over our hem, and it is really the continuation of the original UV map, which is looking really nice. So this is how it was looking before, with just really stretched UVs, and now we get proper continuous UVs. And the final attribute we need will be our custom UV map from before, which was, to remind you, a UV map which is continuously following the curve of the hems. And for this, we will also need a sampled index node, so we can Ctrl-Shift deduplicate all this, but this time we will sample the UV hems from the output of the repeat zone. And now we can capture this value after the one from before and just output it straight away. Let's rename it UV hems and with the default attribute of UV hem. And let's also frame this, label this final attributes. Now if you take a look at this map on the shading tab, we can do some pretty fun stuff with it in the same fashion as what we did on the tutorial on the edge top stitches. So here, if I take the vector output, separate the channels and only use the Y and Z channels, if I put this into a noise texture, I can obtain some continuous noise value which is going on the side of our hems and create an effect of seam puckering, which we can emphasize with the vector math, on which we scale the Y value to crunch everything. And here you can really see that this custom UV map is following our hems, and this can look really nice. But of course this value doesn't exist for the geometry which we didn't process, so for that we can just use an attribute we stored at the beginning of everything to mix between two different colors, for example like this, and this attribute is just called processed. Now we get a black value everywhere where it doesn't exist. But also this value is only relevant on the side of our mesh near the hems, so you can blend between some value to make it disappear. And this is really easy. We can just take our UV hem, multiply it by a vector with 0 on the z-axis to only get the x and y component, and here we can take the length of this vector, which will effectively give us the distance from the edge of our mesh where we made all the hems. Then you can go into a map range node and map, for example, from 0 to 1 centimeter. Then you can put this into a float curve to smooth everything a bit, and we can also use this to mix between a block value and our noise from before, which looks like this in the end. And now if I tweak a few parameters and use this as a bump on our mesh, we can get a really nice seam puckering effect, which is fully procedural and really cheap to compute. And this along our custom UV map, which extends the base UV map on the newly created hems, gives a really nice effect. And most of all, as was the base promise of everything, if we add some displace modifier right before our geometry node, we can check that everything we did is really stable, even if you have some big simulation going on or anything else. Because everything was computed using UV space math, it will always be stable. I hope you liked this tutorial and found something interesting. As usual, the node setup will be available on my Gumroad, and it will be included with the node groups from the top stitch tutorial to continue to work towards a really big cloth making toolbox, which will be fully procedural. Like and subscribe if you want to support me and see more, and see you next time.